Welcome to this invited talk on opportunities and challenges to find sustainable alternatives. I would like to thank the organizers for the invitation. So let me start by setting the reference point. As humans, we are the master of the planet Earth, but what should we do to remain at the top? We need sustainable solutions that is not just improving the environment or social or economic, but a combination of all of these. What are the challenges? We have on Earth the interactions between food, water, energy, environment, and we need to find a sustainable solution. So this talk will highlight the energy, water, food, environment interactions and the challenges and sustainable solutions related to them. Let's look at some of those challenges. The population on Earth, the global population, is expected to reach 10.5 billion. Maybe it will be a little bit lower according to the new estimates, but what will be the consequence of that? We will need global GDP increase of 6 to 7 times. That will require 5 to 6 times increase in production capacity for most commodities, which will require 3.5 times or more energy demand and 7 times more electricity demand. All of these will require increase in water demand, and all of these will increase the global, the greenhouse gas emissions. And this we can see from the data. It's not predictions, actual data. The food demand is increasing. The energy consumption is increasing. The global water consumption is increasing, and all of these increases the CO2 emission. So what is the consequence of this? The average temperature increase on Earth is increasing and increasing at a rapid rate. What will be the consequence of that? The pictures tell the story. No need to explain. So what we need is urgent action. We have to slow down the global warming, reduce the water land contamination, stop the forestry destruction, recover and reuse resources, and many more. How? Please follow the rest of this presentation to get some views that I have. So in the second part, I will define some terms, that is terminology, give some terms of reference, and highlight some selection issues. So as we said, sustainability is the ability to sustain or the capacity to endure changes. Sustainable development a long time ago was defined very nicely in the Brundtland report. Sustainable development, that means the needs and aspirations of the present without compromising the ability of future generations to meet their own needs. The question is, have we been following this? Another way to look at the sustainable development and sustainability is to see this plot on the left. On the y-axis is the human progress on Earth, that if the human progress should be sustainable, the green curve needs to go up. And what we see is that at different periods of time, different technologies were developed, and before they got redundant, another technology took over, so the green curve continuously went up. So the question is it time for the green curve to come down because of the global warming and other effects, or what can we do? So maybe it's time for a new paradigm in technology that can continue the green curve upwards and overcome the problems that we are facing. Let's look at the Sustainable Development Goals as proposed by United Nations a few years ago. There are 17 goals that needs to be satisfied. Of course, we cannot satisfy all of them at the same time or through the same projects. What we have to see is how we can satisfy them so that the curve that you see with respect to climate risks can be flattened. This kind of curve now is very common with respect to COVID-19 infections or death rates, etc. If it is business as usual, the curve will go up and we will have a lot of problems. So just like that, we need to flatten the curve. We need to make sure that the climate risks are below the Earth's capacity, and therefore sustainability is a priority. So chemical engineering should be able to provide the means to find ways to flatten the curve. The question is, what have we managed to do up to now? Let's look at a multi-layered view of chemical engineering, which can give us some ideas. In chemical and I would say biochemical and related engineering, we convert resources to the products and wastes that sustain our society on Earth. To do this, we develop processes, that's it, design processes, control processes, operate, build, and so on. And to do this, we need the fundamental principles. We apply the fundamental principles. That is the core. But is this core enough? With respect to resources, we have demand, availability. With respect to products, we need improved products. We need less waste. In order to achieve this, that will give us sustainable technology, we need expanded or expansion of the fundamental principles, and that we can achieve through a combination of science and engineering. But is that enough? We need more, because the resources are location dependent. There are different types of location, there are different demands, availability, recovery, all of these need to be looked at. With respect to the products, we need optimal products, low waste, controlled environmental impact, and so on. To achieve this, to serve the society, we have the sustainable development. We provide industry, institutions, engineers who can then sustain our society. For this, we need integration of ideas, disciplines, data sources, and so on. So chemical engineering can provide help with problem identification, system versus impact, availability, alternatives evaluation, development of methods and tools, mitigation management. All of these are core or expanded in the middle layer or the final outer layer that are parts of chemical engineering. So now let's see how we will apply that. By system, we mean the system that we have originally or a system that is an alternative. If we want to find whether we have a sustainable alternative, we need to compare the original with the new. So whichever is the system, we need to know all the information that is coming in, not just material and energy, but also money, people, resources, data, everything. We need to know what is going out. We need to also check the waste. If we have all the information with respect to these, which we will see how we can get, we can then calculate what is called indicators or metrics, which can be input, output minus input, that is input is the reference, or ratio. And the list below, you see some of the methods by which we can calculate that, including different kinds of footprints. That will tell us whether an alternative is better than the original. And as an example, I can give you this one that is a little bit old now, that there are impacts related to environment, social, economic. We can calculate if it is output minus input. If it is negative, it's good. If it is positive, it is bad. In the case of material land, if it is close to 1 or low, if we take the ratio of output by input, then as low as possible is good. In terms of profit, economic, social, the way it is calculated, higher than 1 is usually good. So we have the means to check which one is better. Then the question is, how do we look at these? Whenever we have alternatives, can we satisfy all of them, all the criteria, or should we satisfy some? I've seen a lot of publications where there is a trade-off proposed between economic and environmental, and the environmental impacts are summed together as one impact. That is not very good idea, and the reason is that we should not be looking for trade-off. We should be looking for non-trade-off solutions. And just to give an idea that if we take a weighted impact, which would have the same value, high GWP and low toxicity, or vice versa, both of them will have the same value, and either of them is not good. So we need to look at the truly non-trade-off sustainable solution, which is at the lower right-hand side. But if we just look at the profit, it's clear what is going to happen. So how do we find the non-trade-off solutions? I will take three variables: the economics, the environment, the resources. We reduce them. If we are able to reduce them, we increase the profit, we improve the environmental health, we increase the amount of resources left. So there's no trade-off here. How can we achieve this? We improve the energy consumption, that is, reduce the consumption, reduce the water consumption. How can we do this? We improve the efficiency of the system and operation, we reduce the demand. And then when we want to compare, the green boundary is the reference. Any system that is inside the green boundary, by definition, is better. And I would add that at least two of the vertices should be better than the reference. Then we have a truly non-trade-off, more sustainable solution. And these are the ones we should be looking for. And I would claim that it is possible to find them. We do not need the trade-off solutions. So in the third part, I will discuss some of the important issues related to the problem solution. We need a good understanding of the problem, and based on that, develop solution strategies. So since we are talking about process and design and synthesis, we need to look at what are we doing here. As we talked about, we put resources, we put utilities, we get product, we get waste, and we put material, we put knowledge, and also we get waste. So what are the issues? Which raw material to use, which product to make, which utilities to use, how many processing steps, and all these. So we can see that there's a lot of decisions that needs to be made. And those decisions will influence our sustainable solutions. We also have talked about that we humans are the master of this planet because we are able to convert resources to the products that we need, as is shown here. However, to convert resources to useful products, we need to define the products to make, identify the raw material that we can use, and find a process that can manufacture the product in a sustainable manner. However, with the current increase of the global warming and related issues, we can see that order of magnitude improvement is necessary compared to the current state of the art, which means that we should be looking for prevention rather than cure. However, if a process already exists, it is already impacting the environment, we have to cure that. If we are making new, we have to prevent it. So when we are looking for new solutions, we should be looking for prevention. When we are trying to tackle the problem that already exists, we should be looking for cure. But we should not be looking for trade-off solutions, we should be looking for non-trade-off solutions. And obviously, if we want to cure, which is more difficult than to prevent. So let's look at the question of what, why, what to make, why to make, where to make, and how to make. If we look at the tree on the left-hand side, at the lowest end, we have the raw materials that are the resources on Earth, which can be converted to basic products at one level, and then to go higher, we can make intermediate products, and then at the highest, we get the final products that we need. Each step from one level to another needs a process, or more than one process. And as we go higher, the price of the product increases, but the amount of product that needs to be made is less. So there are some correlations between the product and the process we need to know. The tree just shows a small subset of resources. If we look at the curve figure on the right with the earth, we can see a lot more resources that are available on earth. So the question is, are we using all these available resources? Note also that all these resources are not uniformly distributed on earth, which means that solutions are location dependent. What is good for Europe may not be good for other regions in the world, and what is good in other regions of the world may not be good for Europe. So the resources, where they're available, how much they're available, and how they can be converted to the products we need to be looked at. In terms of where we should target from a chemical engineering point of view, and if we are going to target the global warming and the CO2 emission reductions, this curve on the left gives a very nice idea. This is from the International Energy Agency, and they showed what kind of activity is needed to keep the increase of temperature on Earth at a specific level. So then we can see that with respect to power, industry, transport, buildings, and other transformation, if we highlight the industry, we can see significant energy efficiency is needed for the improvement that we need. So we have to identify what we need to do, and the challenge is technological solutions that must be provided within an industrial, social, regulatory, and ethical framework. The table here with the last three columns shows in terms of commodity industry, pharma, bio industry, food and health industry, the kind of products that are obtained from those industries. And we are highlighting here with respect to utilities and waste, we can see that the commodity industry are energy intensive, produces a lot of CO2. There are byproducts. Pharma bio is not energy intensive, but water intensive, has a lot of unused material and also water. With respect to food and health, there are some products that may need energy, like cattle farming to get beef. There are others that are water intensive, a lot of unused material and a lot of water use. So based on this, we can check where have we been targeting to improve. And here I would say that maybe we have lost focus. Instead of trying to find sustainable solutions on energy intensive processes, we have looked at other. We have sustainable business, we have sustainable education, we have sustainable many other things. Unfortunately, the global warming has been increasing. So have we been looking at energy intensive processes? That's a question mark. If we look at some of the publications, I've taken from several journals, a total of 100 publications, recent publications, and listed them in terms of topic and in terms of energy, water, environment, food, all these. What we can see, just to highlight very briefly, there's a lot of papers on CO2 capture and utilization. There's a lot of paper on new processing route alternatives, and so on. So with respect to the new processing alternatives, I will refer to them later. But with respect to CO2 capture, what I would say is that capture technology is very efficient these days. I think very efficiently the CO2 can be captured. The problem is what we do with it. And here is one. Besides sequestration, if one is looking for utilization, unfortunately, that turned out to be not very good. If we look at on the y-axis, the number of power plants, that is in terms of a standard size, and on the x-axis is the chemicals, the world demand of chemicals that would be met through the captured CO2. So what we see is that for dimethyl ether, which has the highest demand for the chemicals that are listed, we need 35 equivalent power plants to produce from the captured CO2 all the dimethyl ether world demand. And for the rest, it's less than 10. So by capturing and utilizing it for other chemicals, unless the demand for these chemicals increases significantly, it's not going to solve the problem. We need to look at it in more detail and find a combination of different alternatives to do that. And I put the question also, what about this CO2 capture is from stationary sources? What about the dynamic sources like direct air capture technology? We talked about that chemical processes are energy intensive, and within that is distillation, but not all distillations consume the same amount of energy. This table is very interesting. It shows which distillation columns for which systems use the most energy. And we can see while there is a lot of plants with respect to hydrocarbons, at least 1, 2, 3, 4, 5, the first 5 systems are the most commonly found in petrochemical and refinery industries. And the remaining ones are the low energy intensive distillation. But a lot of research are actually in the middle ones: water, oxygenated hydrocarbons, aromatics, water, hydrocarbons, and others. These are very, very small amounts. So are we targeting the right processes for energy decrease with distillation? We will see that later. Let's go into the examples, and I will show with the examples which are we targeting and why we should be targeting. So what I would say is that process intensification has been identified as a means to achieve sustainable circular economy. And if we can define the objectives of process intensification properly, we should be able to find improvements in process. And these improvements can be all the improvements we want to reach that we have discussed, and process intensification by different means like reaction path or species allocation or heat and power management, rate size mechanisms, tasks and equipment controllability. All of these will help us to get the improvements we need. In USA, the Rapid Institute has started, or for the last 4 years, have been doing funding projects on PI, and this is a very good initiative to find new alternatives that can achieve sustainable circular economy. The result here would be novel networks, novel integration schemes, new equipment, intensified equipment, new processing routes. All of these can be achieved through PI for the improvements we need. Let me give you some examples. So we know that reactive distillation can represent or can do all the operations needed in a chemical process, like the ones you see on the left. But the question is, are these processes really energy intensive? That means, how much energy do they use? If they don't use appreciable energy, yes, we will find a replacement with a distillation column, a reactive distillation column, but is it improving? So we have to look at that. And if we want to know, identified a intensified intensified process that can be converted to reactive distillation, we want to know, is that possible? The questions on the right-hand side, if the answer is yes to all the questions on the right-hand side, yes, we should be able to find and design a reactive distillation that will significantly improve the chemical process, both in terms of energy and material. So that's an option. The question is, how many of the chemical processes have been converted to reactive distillation? Only a few, probably. So that's one. The other one, we have talked about that hydrocarbon processing is the most energy intensive. So the question is, how many of these columns have been replaced? And I would say probably almost zero. There is a long-term solution that the distillation column in future, when there is a suitable membrane or related material, probably can replace totally the distillation column. In the meantime, the short-term solution would be a hybrid scheme where distillation will be used until it becomes inefficient. Until a certain purity, like 85% purity or 90, between 85 and 90, distillation is very efficient with respect to energy. It cannot be replaced by something else which is more efficient. But from 90 to 99%, distillation is not efficient. So if for that part, we replace distillation with a membrane, which can do this small separation very well, and for that membranes do exist, the solution will be a win-win solution. And by combining the two techniques at their highest efficiency, it is possible to reach 10 to 50% energy consumption decrease or savings. Now, there are 100,000 operating distillation columns on Earth on a conservative basis. The question is, how many have been replaced with this hybrid scheme? This hybrid scheme doesn't require removing the distillation, just adding a small membrane unit, and the cost can be overcome within 3 months from the increased profit. So the question is, are we doing something there? It is still a short term, but it will definitely make an impact on the energy savings and the carbon footprint. The other one is network. It's very popular, this kind of problems. We have the chemical process, but the boundary is not the chemical process only. We also have the power plant and other plants that would supply the needs of the chemical plant. And if we take them together and look at the carbon CO2 emission, we have a problem. But should we use only the fossil fuel, or can we combine with other energy sources to get almost a zero CO2 emission? So energy demanding technologies, which are our processes, need to be combined with energy producing technologies, with the power plants, to find out optimal solution. And here is an example of that. We have the chemical process network. We need to optimize it. We have the network for energy supply. We have the network for water supply, treatment of the water so that it can be recycled also. And together, we want to find the optimal match of to maximize profit, subject to environmental constraints, zero or negative CO2 emissions, safety, health, and so on. Can this be obtained? Yes, we have already solved a problem like that and published it in Computers and Chemical Engineering, but not that this is a local solution, region dependent. The solution that is provided here will be different for exactly the same process in another country, in another region. So the problem definition will need to take them into account. The final problem is chemical substitution. There's a lot of, this is not energy related, but pollution related. We are using a lot of chemicals in the product, in the process. Does those chemicals satisfy the REACH or US EPA regulations? If not, what can we do? There's a step-by-step process. Identify the chemicals, find out if there are any contaminants. If there are, then substitute it. If there are not, verify the product, certify the product. What do we need to do this? We need a large database so that we can identify which are the contaminant chemicals, what are their properties, and then we need to find out ways to replace them. There are tools already available for doing this. And this is very interesting because what is shown here is the periodic table, but the red boxes are the rare earth metals, which people have predicted that within the next 5 to 50 years, they might not exist anymore. So we have urgent need to either find more of these or replace them. And just think of what would happen if some of the more populated countries decide to have more cars than the less populated countries or highly developed countries. Then we will not have enough metal for all the people who want cars. So that's something to think about. So finally, perspectives and conclusions. Turning challenges into opportunities. We have challenges with water, resources, food, health, energy. We have issues on Earth. That is issues. Earth resources are not uniformly distributed. We need to find sustainable solutions which are region dependent, and technologies that therefore would be region dependent. That is, the application of the technology will be the same technology can be applied in different places, but how they are applied needs to look at the regional limitations. Example, non-renewable resources for energy fossil fuel are commonly used even though they have the highest greenhouse gas emissions, because the technology is well developed and therefore cheap. Solar energy, on the other hand, is abundantly available in some regions, do not negatively affect the environment, but the technology is still expensive. They're becoming less expensive. So an optimal combination needs to be found so that we have a zero CO2 emission. And similar issues are also encountered with other resources. So we need to find a good combination of resources together with all the other things. Finally, I want to say that all the things that I've mentioned as solutions, the question is, do we have the methods and tools to get them? And we can see that in order to find the new kind of solutions, we need library of databases, because we need a lot of data, a lot of knowledge that can be captured in terms of information and kept in the databases. So big data, machine learning, all of these are important. We need new models for flow sheets, properties, for new operations. All of these things, the models do not exist. We need to develop them or develop them in a online way, interactive way. Then we need new synthesis methods, not only to convert processes in resources into products, but also intensified options, hybrid options, and so on. And if we have all of that and we have the models, we can perform the simulation of the process. And from the generated data that I showed before, we can calculate, use the utility and analysis tools to calculate the different indicators to decide which one is better. Now, from all of this, we can see that only one task, that is simulation, process simulators, they only perform one of these many tasks. The question is, do we have all the other tools that are needed, and how are they integrated together with the simulator? That is also something that needs further development. Finally, I will highlight the role of chemical engineering and say that chemical and biochemical engineering and related disciplines, we need to promote research and development as a fundamental pillar and encourage technology development to achieve a planet able to sustain a growing population while improving quality of life. Facilitate global dissemination of chemical and biochemical engineering technical knowledge and industrial best practices, striving to bring together academia and industry worldwide. Promote conservation and care of global resources, health, safety, and the environment. Promote the high standards of professional ethics and conduct for chemical and biochemical engineers worldwide to safeguard the public. Prepare for the next pandemic or disaster with methods and tools that can contribute to quick problem solution, contribute to sustainable development. With this, I thank the organizers again, and I finish my lecture. Thank you very much.